Hey guys, I wanted to give you an introduction to light, which is going to be our obviously our last unit in the whole physics course. Generally, we would do a light unit and then also a unit on electricity and magnetism, but obviously we're moving at a much slower pace. We don't have time for labs and things like that, but there is a lab that I want us to do that goes along with this one. Hopefully, we'll be able to do that one next week. It's one that you can do from home with just a microwave and either chocolate or marshmallows or Peeps or something like that. I'll explain that more next week. But if you do go to the store within the next couple days, or someone's going grocery shopping or doing Instacart or whatever, um, make sure that you put a chocolate bar or some marshmallows on there. Okay, so I wanted to give you a introduction to light here. I want to talk about a couple things, sort of the nature and history of light, and also about the speed of light. And our next big thing will be about light reflection. But what is light? Where does light come from? We can think about it in sort of a physical nature. Where's the light actually? What physical property does light come from? We know that light is electromagnetic waves, which we'll talk about in a little bit. But how is it actually produced? We know things that are hot kind of produce light, but there's really three ways that light can be produced. Light can be produced by any hot object. We call this thermal radiation. So once there's a certain threshold is crossed, something starts to emit visible light. Now, we know from infrared cameras and things like that anything that's, any temperature produces its own light. It just may not be in the visible spectrum, but thermal radiation is one. Absorption and emission are two that you probably talked about in your chemistry class, that certain elements or certain substances can absorb certain frequencies or emit certain frequencies. And it turns out that the frequencies of light that they absorbed and emit are the same depending on the substance. So I'll come back to this idea, but so a thermal radiation is like the original Edison bulb, or like the element, like if you have an electric stove, or if you ever put a hot poker in a campfire, something like that, that you notice it gives off its own light. The reason it does this is what's called black body radiation. The molecules, the atoms themselves, are vibrating at such and such a frequency depending on the temperature. And so the hotter it gets, the more sort of yellow and eventually white hot it gets. Whereas when it's a little bit cooler, you can see kind of the edge of this iron. It gets sort of a deeper red, and eventually what looks like black, but probably is actually infrared radiation. We call this black body because it doesn't matter what color the filament it was before you turned it on, or what color the iron was before you heated it up, because the color that it produces is independent of its paint color or whatever. So we just take them all to be black, other than the color that they're emitting based on their temperature. But the other two ways that we see light are from, like on a more atomic level. So the sun and other stars would be a great example of what's called absorption spectra. If you pointed a telescope at the sun, if you had a proper filter on it, and you were to sort of spread out the colors that you see from the sun, you would realize that you are actually missing certain frequencies. They're missing certain colors of light. That's because of the sun's absorption spectrum. The sun sort of scatters its own light because of its exterior. Most of the heat and light from the sun is actually produced in the interior, and the exterior of the sun sort of scatters away certain frequencies. So if there was no outer atmosphere on the sun, it probably wouldn't work correctly, but if we could see the sun's hot interior, it would just be a continuous rainbow sort of peaking in the yellow because of its temperature, but we wouldn't see these missing colors if it's not for the cooler outer atmosphere of the sun. But then we have what's called the emission spectra. So these lines are based on what elements are within the sun. The sun is 75% hydrogen, and the other 25% is mostly helium, although there are some other elements in there. So we would see these lines based on the elements that are in there, which I'll talk about in just a second. The other way that we see it is with things like neon lights and fireworks, that certain colors can be produced by certain elements if you just excite that element only. So neon lights if they're truly the element neon, will produce in sort of an orange-red color. And so they will only produce certain frequencies. Coincidentally, these are the same frequencies that would be absorbed by neon if light was passed through neon. But every element can sort of produce its own frequency of light, its own wavelength of light. And so sort of the yellow lights tend to come from sodium, and blue lights can be like argon or krypton. So different elements produce different colors, and fireworks are the same way. It just depends on what elements are inside of them are emitting their own wavelengths. Well, why does this happen? Why do we see certain colors from certain elements, whether they're being absorbed in the case of the sun's cooler exterior, or emitted in the case of neon lights and fireworks? Well, this has to do with something you probably learned in chemistry. I hope you learned it in chemistry because it's sort of fundamental. We can remember that electrons are orbiting on the outside of atoms, and we also remember from the Bohr model that they're in different energy levels. And so when they absorb energy, they always jump to a higher energy level, but that's only sort of like quasi-stable. They'll eventually fall back down to a lower energy level. And whatever the energy difference is between the inner and outer level, they'll eventually re-emit that exact amount of energy in the form of light. Now, depending on if it's a very large transition from going from a very low energy, very high energy, that will be a very high energy particle of light that's emitted. And this is called a photon. Photon meaning photo particle or light particle that's being produced here. So this is how elements produce light sort of on their own with excitation there. And so we can sort of make a calculation here about how much energy is there, and there's a conversion that you can go from an energy difference to an actual amount of light. And so just going for something like hydrogen, you can predict there's very specific colors that would be produced by hydrogen. Okay, this is why we see the sun producing, or rather scattering, certain wavelengths, because it's got so much hydrogen in it. You can tell with very bright hydrogen. So this is what we would call a spectral fingerprint, where every element kind of produces or absorbs these certain frequencies. So it can go either way. The frequency, in order to jump up to this energy level, it needs to absorb a certain frequency, and then when it falls back down, it releases that certain frequency. So depending on if the energy is coming in or going out, you'll still see that same frequency of light either being absorbed or emitted, but they're not. It's not like there's two different spectra. They're the same. It's just one is missing and one is the only thing that's present. So that's how light's produced. And so we can sort of match up different patterns of wavelengths to different elements. Helium, hydrogen. So this is really one of the only ways. There's a whole branch of astronomy related to, or a whole branch of physics called astrophysics, where really what you're looking at is what stars and other things like that are made of on an atomic level. And that's a major part of astrophysics, is comparing these sort of spectra of light from different elements. The other thing I wanted to talk about in this lesson is how light travels. So that has to do with partially with the spectrum of light and also a little bit about the speed of light. So in the 1800s, people began to make a couple different realizations about light. One of them was, so Isaac Newton had already in the 1700s discovered that white light is actually a combination of the rainbow. That's where we get kind of the Roy G. Biv, red, orange, yellow, green, blue, violet. And it was about 100 to 150 years later that people discovered that there were other invisible forms of light. An astronomer named William Herschel discovered that beyond red, or just lurking below red, there was infrared light. He did this with an experiment where he was trying to measure the temperatures of light by color, and he had a control group thermometer sitting outside of the red, which actually got hotter than any of the ones sitting within the visible light. So he named this below red. So you realize that there actually was light, he just couldn't see it. So that was in the 1800s or early 1800s. And then Heinrich Hertz was one person that realized that that light is actually, all light is actually part of the same type of fields. It's part of these electric and magnetic fields that are oscillating. And we said that these are transverse waves because they're oscillating perpendicular to the way that they're traveling. So a lot of people made some kind of claims about what light really was, but we know now that it's visible light is really just one sort of piece of the entire spectrum. So visible light is a very small band of light. If I look at all the different, I'll go back up in a second. If I go back up, it's really only 700 nanometers for the lowest, darkest red light on the verge of infrared to 400 nanometers for violet light on the verge of ultraviolet. But there's an incredible range of wavelengths for light, and the shortest being gamma ray and the longest being radio waves, where we have a radio wave can be up to like over a kilometer long, whereas a gamma ray is smaller than a proton or a neutron. So we have an incredible difference in sizes of waves, but visible light is really just one really small section. There are actually 7 classifications of light, as I just showed you. You should understand that visible light is sort of in the center of that. Radio waves are the longest waves, and gamma rays are the shortest waves, which are also the highest frequency. We can remember our frequency wave relation that the speed of a wave is equal to its frequency times its wavelength. So as a wave gets shorter, as the wavelength gets shorter, the frequency has to get higher. So a short wave, like a gamma ray, has to have a very high frequency. But we know that all forms of light travel at the same speed, which we just call the speed of light, which is always represented by the letter c. So c for all forms of visible light, or all forms of light, visible or invisible, is always the same speed, which is 3 times 10 to the 8 meters per second, which is 300,000 kilometers per second, or 300 million meters per second, which is incredibly fast. And I always wondered, how do we know what the speed is and how do we measure it? So there's something that I want you to watch. I would sort of demonstrate how we found the speed of light. The first experiment discovering the speed of light was in the 1600s by a man named Ole Rømer, who was a Danish astronomer. And a more modern measurement of the speed of light was by a person named Fizeau, Hippolyte Fizeau, was redone by a guy named Leon Foucault, which we've talked about Foucault's pendulum before. He was just a very important physicist in the 1800s. So I'm going to post the link to this on Classroom as well, so that this is going to be the follow-up second part of the lesson. There's another physics teacher who does a very good explanation of the different ways that we measured the speed of light. So that will be the extent of our lesson for this week.